Now, some of you may be thinking, well, when we talked about two proportions and we were comparing them, we pooled when we were talking about comparing those two. So remember, with tests for proportions, we know the standard error for the sampling distribution. So testing the null hypothesis that our two proportions are equal, we assumed that the variances must be equal as well. That allowed us to pool the data for the hypothesis test. And for means, there is also a pooled t-test. So like two proportion z-test, this is a test is used when we assume that the variances in the two groups are equal. But we must be careful, as there is no direct connection between a mean and the value of the standard deviation. If we're willing to assume that variances of two distributions are equal, we can pool the data from two groups to improve our estimate of the population variance and make the degrees of freedom formula much simpler. I'm just going to make a note. This is seldom used. So once we have that note, let's proceed. We're still estimating the pooled standard deviation from the data. So we use student's t-model, and the test is called a pooled t-test for this difference between means. And we've seen that as an option on our calculators. If we assume that the variances are equal, we can estimate the common variance from the numbers we already have. We look at our variance, our standard deviation squared of pools, is we take the first sample minus 1 squared plus the second sample minus 1 squared times the standard error times the standard deviation over the sum of n1 minus 1 plus n2 minus 1, which gives us our standard error formula, which we take our s pooled, which is the square root of what we just had, times the square root of 1 over n1 plus 1 over n2. Noticing that our degrees of freedom becomes n1 plus n2 minus 2, which comes from our denominator. The conditions for a pooled t-test and corresponding confidence interval are the same as for our earlier two-sample t procedures, with the additional assumption that the variance of the two groups are the same. So our hypothesis test, the calculated test statistic, is our t-score, which we have the difference in our sample averages minus the difference in our hypothesis mean over our pooled standard error. So s times the square root of 1 over n1 plus 1 over n2, with the degrees of freedom of n1 plus n2 minus 2. The confidence interval would be the difference in our averages plus or minus our critical value with the degrees of freedom times our standard error for our pooled. So now that I've told you all of that, when should you use the pooled t-test methodology rather than the usual two-sample t-test? Never. Okay, rarely. But rarely to never are we going to use the pooled t-test. Because the advantages of pooling are small, and you should pool only rarely when the equal variance assumption is met, we do not pool. It is never wrong not to pool. Not pooling is actually a more conservative test or interval. A wider interval, more difficult to reject the null hypothesis. So what do you say we make this real simple? When comparing means, do not pool. Only pool for two proportions. Do not pool for means, only pool for two proportions. Got it? There is a hypothesis test that will test for homogeneity of variance, aka equal variance. The homogeneity of variance test is very sensitive to failures of the necessary assumptions and is not reliable for small sample sizes. Since those are the conditions for which we need the two-sample t-test, there's not much justification for pooling. Thus, the test is unreliable under the conditions most affected by pooling and when we would most like to pool. So is there a place for pooling variances from two groups? You betcha. In a randomized comparative experiment, we begin by randomly assigning experimental units to treatments. So each treatment group comes from the same population, and thus begins with the same population variance. In such a case, assuming the variances are equal is a plausible assumption. But there are conditions that still need to be verified to justify the assumption of equal variance. We ain't going to go there, so just know we are not going to be pooling when we're comparing means. Some words of caution. Do not assume that because you have two samples, you then have two independent samples. The independent group assumption deserves some attention. If the samples are not independent, you cannot use two-sample statistical methods. Check the histograms of your samples. Check for outliers and deviation from unimodal and symmetric. We have not yet talked about paired data, or matched pairs. That will be the new, much simpler test. Matched pairs tests do not have independent groups. Until then, make certain your samples are independent. So until we get to chapter 25, make sure your samples are independent. Additionally, the difference between two means and the mean of differences are most assuredly not the same. Know which you have. Make certain your groups are independent when you use the two-sample t-test. And that is the key. Make sure, I'm going to underline this, make sure your groups are independent when you use the two-sample t-test. So let's try one last example. Resting pulse rates for a random sample of 26 smokers had a mean of 80 beats per minute and a standard deviation of 5 beats per minute. Among 32 randomly chosen non-smokers, the values were 74 beats per minute with a standard deviation of 6 beats per minute. Both sets of data were roughly symmetric and had no outliers. Is there evidence of a difference in mean pulse rate between smokers and non-smokers? And if so, how big of a difference? So let's look at this. We are to test the difference between sample means and compare to a hypothesized difference of 0. So let's write out our hypothesis. So our null hypothesis is saying that the mean beats per minute for our smokers is equal to the mean beats per minute for non-smokers. Or another way of writing it, the difference between the means is equal to 0. Our alternative hypothesis is that they are not equal to each other, or the difference in the two means is not equal to 0, which would entail a two-tailed test. Now we check our assumptions and conditions. So our independence assumption, we check randomness. Both samples says were randomly selected. Our independence condition, the participants in both samples are independent, smokers or non-smokers. 10% condition, we could likely assume 26 and 32 are less than 10% of the population of smokers and non-smokers alike. Next, we look at our normal population assumption, and we are told that both samples are roughly symmetric, so that takes care of our sufficiently normal condition. Lastly, independent groups assumption. The two groups are obviously independent of each other. So from there, we're going to conduct a two-sample t-test with our normal model with a hypothesized mean of 0 and our standard deviation of 1.4445. Make sure you look back to see how to calculate the standard error. Now, before we move on, we're also looking at an alpha level of 0.05 and a critical value, which will come from our degrees of freedom. So let's jump to our calculator. So we're going to hit Menu, Stats, and then we're going to go down to Tests and do a two-tailed t-test. We're going to select Stats. We're going to type in our averages. So x1, the average is 80 with a standard deviation of 5 and a sample size of 26. Our average for our non-smoker group was 74 beats per minute with a standard deviation of 6 and a sample size of 32. We're testing our alternative that they're not equal to, and we are not pooling. And when we calculate that, we get our p-value of 1.12 times 10 to the negative fourth, or e negative 4. We get our degrees of freedom of 55.95. Now those are the two values that I want you to make note of. Because once we get our degrees of freedom from our calculator, we can also calculate our critical value for 55.953 by using inverse t. And we're using a alpha level of 0.05, so we go second, stats, distributions, inverse t, 0.975, and our degrees of freedom is 55.953, which gives us a t critical value of 2.033. Before we come to our conclusion, let's make sure that we write out our calculations. So we find our t-score by taking the difference in our averages, so 80 minus 74, minus our hypothesized mean of 0, divided by the standard error, which is s1 squared over n1 plus s2 squared over n2. When we do that, we get our t-score of 4.1537. You do not have to calculate the degrees of freedom by hand, but here is the calculation. So what we are looking at is what is the probability that we get a t-score that's greater than 4.1537, or what's the likelihood that 4.1537 is greater than 2.0 that we calculated for a critical value. So what's our p-value? Well, we saw that our p-value is 1.12 times 10 to the negative fourth. So we're going to draw our picture, and we have a two-tailed test. We're comparing this against our critical value that we found from our degrees of freedom, and we have our two areas on either side. So what is the likelihood that we get that? 0.0001. So this is the probability statement. What's the probability that t is less than negative 4.15 or greater than 4.15? Or what's the probability that the difference in our means is greater than 5276? Which is 0.0001. So note that our decision that the probability is less than our significance level, or our t-score is greater than our critical value, so we must reject the null hypothesis. We come to our conclusion. There is sufficient evidence to suggest a difference in mean resting pulse rates for smokers and non-smokers. The data indicate that the mean pulse rate for non-smokers is lower than the mean pulse rate for smokers. Now, the second part of the question says, how big? So that's when we're going to jump to our confidence interval. We will find a 95% confidence t-interval for the difference between mean pulse rates with the model. This is our difference now. That's y1 bar minus y2 bar, and our standard error that we found before. We've already checked the assumptions, so we can jump straight to our calculator with our critical value that we found earlier. So 80 minus 74 is 6, plus or minus 2.0033 times the square root of our standard error. So we get 6 plus or minus 2.8937, or a lower bound of 3.1063 to 8.8937. Now going to our calculator, we're going to go hit Menu, Stats, Confidence Interval, and we're going to do a 2-sample t-interval. We're going to type in our averages, type in our standard deviations, type in our confidence interval of 0.95, and hit Enter. So once we have our information from our calculator, we're going to have our two final conclusions. We can be 95% confident that the average pulse rate for smokers is between 3.1 and 8.9 beats per minute higher than for non-smokers. And then we will conclude, finally, by interpreting that 95% confidence interval. If we were to repeatedly sample 26 smokers and 32 non-smokers, 95% of calculated intervals would capture the true difference in the mean population. So that takes us to the end of chapter 24. We have one more chapter to end out unit 6, and then we're done.